Lab 4 Oscillations. In this lab, we look at a spring mass system and try to describe the motion of how the mass swings in a circle while oscillating on a spring. We accomplish this by using tracker and creating a computational model to predict the motion of mass oscillating vertically. The results of this lab allow us to compare the observed and predicted model and analyze several other forms of energy. And by understanding how we can describe this seemingly complex motion, we can apply the physics principles to find real-world examples, such as extreme sports like bungee jumping. So the physics principle that we'll be using is Newton's second law for swinging rope, which is F net, which equals spring force plus gravitational force. And the energy principle is change in energy equals W plus change in Q, but we're ignoring change in Q because there's no exchange of thermal energy. And change in E includes kinetic energy, gravitational potential energy, and spring potential energy. So the formula for spring force is negative Ks times L, and S is basically the change in length, which is the magnitude of L minus L naught. T is the period of oscillation, and based off that formula, you can actually derive this K value, which is the stiffness constant. Now, the initial conditions is basically t equals 0 seconds. The initial velocity is 0, meters per second squared. The mass is 0.402 kilograms, and the length of calibration is 0.7 meters. And basically on tracker, I pointed everything, and this is the graph that I got. And to find the t value, we basically take 3 oscillations in the time period for it, and we divide by 3 and we get a value of 1.519, and then we put that into the stiffness constant equation, and then we get a 6.878 newtons per meter. And based off that, we can derive the L naught, which is 0.127 meters. So the energy principle interaction. So the system is mass plus spring plus earth. There is no work, so there's no energy transfer. So the change in energy equals 0. K equals 1/2 mv squared. Gravitational potential energy is mgh. Spring potential energy is 1/2 ks squared. Now here's the computational model. So as you can see, the ball mass is 0.402. The ball position, which we got from tracker, is inputted. The velocity is 0. And the delta t is 1/210. G, ks, and L naught were already arrived. And this is the value of K, UG, US, and then E, which is a summation of the 3. Now here is gravitational force, which is mass times G times the vector 0, -1, 0, F spring, F net, which is F grav plus F spring. Here's the momentum principle with an updated velocity and position. Now the spring potential energy, the spring force is L and L hat times S. So we're given all of that, and then energy changes is given like K equals 1/2 mv squared. Then delta K is just a change. UG is ball mass times G times ball position of the Y. Delta UG is change, and then spring force is 0.5 ks s squared. And then delta E is a change in E, and then E is just a summation of the 3. Now, when you run this program, you have to input your CSV file from the tracker, and I already did all of that. So I'm just going to give you the graphs that it outputted. So the energy principle is satisfied as change in energy is always 0 and constant, because change in E, which is change in K plus change in UG plus change in US, and there is no external work done, so that equals 0, and change in energy equals work, so change in energy is also equivalent to 0. Now, another what does it mean is basically finding the oscillation period using x position versus y position. So when I use x position, I actually get a k value of 6.092, and when I use y, which I already derived before, I get a k value of 6.878. Now, if you look at the x position graph versus the y position graph, there's more variability in x position instead of y position. And this is probably because, first off, the y probably yields more accurate results, and the y is basically where the mass was changing in the y direction, because for the x position, it was just moving left and right. So there is a difference between them, and y seems to be more accurate because there's less of a difference. Now, in future attempts of the lab, because the period of oscillation varies slightly, we could input more tracker points in order to increase accuracy. And the lab also possesses like some computational inaccuracies, since we're using a basic algorithm, so we can add more stuff to the Newton's second law algorithm, like F drag, which will make the observation and the experimental match.